All right. Any questions? All right, so these slides, in some ways we've done already, right? I made these slides and then I realized, yeah, they're important. So as we've been talking, we've been doing these slides already, right? It's how to brute force the table, right? I claim that you can solve these test questions if you've memorized the purple table and you just have no thinking whatsoever, all right? And what's brute force is you use muscle without thinking, right? And that's what we're how we're arguing. All right, so Hilbert, why are we bringing Hilbert in here? Oh, he's a famous logician, and he was like, can you prove everything? Can you not prove everything? Can you compute everything? Can you not compute everything? He was sort of asking that, right? And so I guess I brought Hilbert in here. So a statement might, if it's true, if it's a tautology, then it should have a proof, right? We would like our proof system to be complete, meaning anything that's true in every universe you can prove, right? So it might have a proof, but it could be hard to find, right? Now, once you have the proof, it should be easy to check, right? But finding it can be hard. Why? Because there's an exponential number of possible proofs, right? So when we say, hey, you look at my solution set and you read it and it's easy, well, that's because the second statement's saying checking a proof is easy, right? It doesn't mean that finding it's easy, right? How do you find it, right? George says don't use intuition. Well, then what do you got left, right? You got brute force. All right. So I'm saying before you try to prove something, try to get some intuition as to why it should be true or not, right? And that intuition can guide you, right? Or you can just brute force it, right? And what does brute force means is on the test, I gave you a bunch of axioms, and you just apply every rule in any possible way, right? You, for each pair of rules, you say, what rule can I use, right? And you just say, those give me this, and those give me this, and those give me this. And you just brute force it. Hear what I'm saying? Just do every rule possible. And then you can go the other direction. I need to produce this. What do I need to produce this? Well, that's this side of the column of the table, right? Says, well, if I know these things, then I get this, right? If I know these things, I get this, right? Now, the only thing that's hard about brute forcing backwards is you have to keep track of sort of ands and ors, right? If I brute force this way, then I need this and this to get this. But if I brute force this way, I need this and this to get this. So really, what do I need? I need this and this, or I need this and this, right? So you got to kind of keep track of that. It's a little tricky. But everybody kind of see what we're doing? Now, where does intuition come in this picture? Intuition says, I kind of understand why it's true, right? And why it's true is that there's this purple statement in the middle, right? Here's another statement that I'm writing down that I'm claiming I think follows from these. What's true about this purple dot is I think I should be able to get it from these, and I think I should be able to get these from the purple dot, right? And you're just leaping in the middle. And then you try to link the two up, right? Does that make sense? And my bet is on the test that you're doing things, you won't have to do this, right? You brute force this way, you brute force this way, they're applied, right? Why does the brute force not work in general? Is because you go this way and it grows exponentially. You go this way, it grows exponentially. And you just can't do them all, right? And by having this intuition, it kind of cuts, right? If I have intuition like this and I kind of cut it in half, I do some serious damage to my exponential, right? Right? Right, this is what I'm saying. For a little small problem, you throw things at it. You can't go wrong, right? Oh, I don't know if I've said this. Maybe I should make a slide about it. What I often see when I mark things is they do this yellow forward, they do this green backwards, and then what's in between, it's supposed to be a link up, but they just don't know how to do it, and they just leave it there, and they expect the marker to, what they hope is that the marker won't notice that there was a leap here, right? And that's one of the reasons we say where all your rules come from, is because we can check it without noticing there's a leap. And I hate it when I see people do this, because I think they're pulling a fast one on me, right? Now, how do we get from here to here? Proof by magic, right? So what I would prefer to people be is let's all keep being honest. And if you get to here and you get to here and you're stuck, you just say, oops, I'm stuck. Let's put proof by magic here, right? And if I have seen that a few times, and it impresses me. And you want to impress your marker, right? All right, so if you brute force it, you're going to have a much bigger thing, much bigger proof than you need, right? And so you can clean it up afterwards. We're out of time. All right. All right, so we're going to need another class on this stuff, and have a good until Wednesday. All right. Oh, you're still not pictures. There we go. All right, so let me tell you about my morning. First, the pipes in my basement burst and water was flooding everywhere. And so I left about 10 minutes late. And then the subway stopped. Something froze. Last class, we talked about some of the difference between our logic, where things are true and false, and our real life. And people were a little confused about it after class. So I made more slides. And I'm not, now that we're late, I'm not sure how much to go over them. But basically, if you prove a contradiction, then you've broken the logic. And then everything becomes true. Their negations become true. So everything is both true and false. And right, so we kind of did that. And I sort of said that knowing the first axiom is true eliminates some universes, and we prove in all the remaining universes that I study. And knowing the second axiom is true eliminates different universes, so in the remaining universes you don't study. And so knowing both, it eliminates all universes. And if you have no universes, then all the elephants in them are pink and everything is true. So just to go back to what our logic is and isn't, people might say, in my life, I can study on one day and not study on another. But in our logic, we don't have time. You could have study, but here we do it or don't do it. You might say you likely study, but we have no probabilities. You might say, I believe I will study, right? But no beliefs. And here's another difference, right? You might say in your life, well, 99% chance I'll study. Well, that assumes that there's a random distribution under there. Well, in our world, we have to be 100% sure. And so we will often talk about an adversary choosing things for us, because if we want to be 100% sure, then you're sure even when an adversary is choosing for you, right? And I talked about stories, but you can kind of read this on your own if you care. And that's those new slides. Any thoughts about anything? All right, so now we'll do some more example proofs. People periodically, the most common question I have is, right, what should I do to study for the test? What will be on the test? And I haven't made up the test yet. And my goal is that my lectures, my slides are so brilliant that you learn everything you need for the test. But it's good to do practice, and there's some practice online, and if you've really done all those practices, we can try to find more. But we're going to just go through some examples of proofs. All right, so and the proofs are all designed to demonstrate various things, right? So here we're going to demonstrate sort of cases, right? Here's a statement that you have this little polynomial here, and it's talking about where its roots are. And so remember, we'll give you some axioms, and then we'll give you some something to prove. Here, there are no really axioms except how mathematics works. And I've started just this last, in fact, this might be the first time I'm teaching it with this, where we split the proof into what I know and what we don't know, right? So down here is what we need to prove. And then you look at the parse tree to see what's at the last thing that gets done. What is this statement about? It's about an implies, right? So you look up in the table, implies, if you want to prove something from implies, what can you do, right? You can, oh, no, this is where you want to prove, how do you improve an implies, right? How do you prove implies? Well, you can build it from other things, or you can do deduction, right? And so which one do you think we're going to do here? How do we prove this, right? We're going to use deduction, right? And so remember how we can build from the top and the bottom at the same time. So here I've kind of outlined the whole deduction proof, right? My goal is to prove this implies down here. So what do? I indent, and I have the left-hand side as an assumption. And then somehow within this indent, right, while I'm still indented, I'm going to prove the right-hand side. And then that gives me left-hand side, gives me right-hand side. Is everybody with me here? Right? All right, so then we can either work from the bottom up or the top down, whichever you feel. And, I don't know what to do with this down here. So let's go to the top. We have an or, and we look at the table. We're using an or, and what are the various things? This is all my friends saying, oh, sorry that you're running late for class. All right, so now what can we do for an or? Well, if we could eliminate one possibility, then we would know it was the other possibility, right? But I don't know how we're going to do that. So, otherwise, and as I said, the motivation of this problem is to look at cases, right? So if we're going to prove it by cases, then we plug in sort of, what's our case goal? That's our case goal, right? What are we trying to prove by cases? Is that statement down there, right? And then what are our cases? Up here, we have an or, it tells us there are two cases, right? So in the first case, we know that x equals 2, so you plug it in, and you get, sure enough, you get what we want. And then in case 2, you plug it in, and you get what you want. And then you conclude this by cases, right? We have the or, the one implies, the other implies. Right, everybody get that? This is just what you did in high school, right? All right, and then you can drop out the statement, right? And I think on a test, you could start having this line be a line 100 if you want, right? Because you're doing it as you go. You don't know what it's going to be. Any questions about that? All right. So I just make up ugly examples, right? Here's an example where you look at it. I'm trying to prove this, and I don't know what that means, right? You can try to think about intuition, what it means, or you could just bang out the proof, right? What's the main statement here? Everybody see at the bottom? It's implies, right? How do you do implies? Well, it's probably deduction. So we assume the left side, and we get the right side. We look at this little character. What's that? Oh, that's an and, right? So we can see what can we do with ands. Well, pretty much always you got an and, you might as well separate them, right? And then we have an implies here. How do you prove, right? So, right, we could work from the top, right? What can we do with this and what can we do with this? But I know this is what I'm looking for, so we might as well get some sense of where we're going, right? It's an implies. So how do you prove implies? You do it by deduction, right? Am I losing anybody here? Everybody good, right? We're trying to prove this. So what we're going to do, we're going to say, by deduction, we're going to try to prove this. So what do we do? We assume the left-hand side, and we have to prove the right-hand side, and that will give us what we want here. Right? Everybody see that? And one thing you'll notice about this pattern is when we work backwards, see, I have this line here that I want to prove, but I don't know how I'm going to prove it. Right? So I have that as a mystery now. And then when I work backwards, oh, now I know how I'm going to prove this. I'm going to first do this stuff, and then that's going to give it to me. But you see this statement here, I don't know how I'm going to do it. Why don't I know how to do it? Because I don't know how I'm going to do it yet, right? Everybody with us here? But we've got down, now we know 3 things. We know 3, 4, and 6, and we have to prove 9. Right? All right, so what do we do now? We can say, well, this has a not gamma in it, and this has a gamma in it with an or. What rule do we use for these 2 yellow things, circles? Right? We have an or, and we have a not gamma. What rules do we use? Come on, guys. Yeah? No, deduction is implies. If I know this or this is true, and, oh, look it, I know the right one's not true, then what do I know? I know not beta is true, right? You look it up in the table. How do I use this or? Well, one way to use the or is by selecting from an or, right? You should learn these guys, right? So here, from 4 and from 6, selecting or gives me 7. Yeah? Oh, yes. Yes. In fact, I think on 2 different classes, I said clearly that on my the first test of my last term, I not only made them memorize it, but they had to, I gave them a blank form and they filled it in, right? And then they went further and had a little discussion about each one. Absolutely have to memorize these, right? And you could say, come on, Jeff, you should give them to us. And I would say, come on, guys, you should have learned them in kindergarten. All right? Everybody try going home to their little kids and ask them if they know these rules. Everybody good here? All right. So now, what do we have it? Another thing what's the difference between when you're doing your PhD and when you're doing test 1? PhD, there's so many facts, and you don't know which facts are going to be useful to you, right? But you can almost just be assured that the thing I'm going to give you is going to be nice and tight, right? If I give you things that you don't need, it will be because I'm trying to be a little meaner to you. And I'm not saying I'm never mean to you. I might be, right? But you can also think, well, if you give it to me, probably there's a use for it, right? So we haven't used, what haven't we used yet? We haven't used 3, and we just got 7. So what are we going to do with those, right? Anybody see how do we combine these? Yeah. 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 It's yeah. Exactly. Exactly. All right. So Modus Ponens says that if you know alpha implies beta and you got alpha, then you got beta, right? But here we got it. This is a beta over here, and it's on the wrong side, right? But we also, the contrapositive can turn this into this, right? So we can first use the contrapositive, and then we can use modus ponens, right? Here's modus ponens from 7, not beta, and 8, right? Does that make sense? Now, I was teaching 1019, as you know, all of a sudden. And one of the things that I learned from the book is that there's another thing, not called modus ponens, but modus ponens or something. Tollens? All right. All right, so what is that? That's combining these 2 steps into one, right? That says if you have this and you have not beta, then you can get now alpha, all right? So if you want to do it with modus tollens or whatever it is, I suppose you could, but I think the intuition is better this way, and you do it in 2 steps, and I didn't want to add it to the purple table, right? Everybody got this proof? Right? So these are the kind of things that you're going to need to do, right? And is the proof unique? No, sometimes there are other ways of doing it, all right? So here we're back to where we were before, right? And we can think, how do we use an implies? How do we get an implies? Well, there's transitivity, right? This says, you're right, it's kind of here, alpha links beta and beta links gamma, so alpha links gamma, right? You can see there's almost transitivity there, right? People with me here? Right? Now, alpha implies, but we're going in the other direction, right? So you can take the alpha implies beta and get beta, not beta implies not alpha, right? And then what about this guy here? Well, we look at this rule again, and it can give us that not gamma gives us not beta, and then you kind of combine these now, right? Now we can get what we want, right? Everybody good with that? So one thing that I don't know if I've said, people like George who want a really nice tight proof system, they pride themselves on having as few rules as possible, right? And I pride myself in having as many rules as will be useful, right? So are there more than one ways of doing things? Yeah. Everybody good? All right. So I had when I was a graduate student, a fellow buddy of mine was working on proof systems and proving that this type of proof system required a really long proof. And one of the key rules of a proof system was called resolution. And this is what the resolution is. It's called the cut rule. Cut rule is what you've stated here is a bunch of clauses, the end of a bunch of clauses, and each clause is the or of a bunch of literals, right? And if you have two clauses that have, here they have a common P, right? This one has a not P in it, this one has a P in it. Then you can cut the P out like this, right? And how do you know you can do this? And well, it was never obvious to me why you could do this, but you have proofs like this, right? Everybody follow what we're doing? We got some statement, we want to prove it, right? So how do you prove it? It implies, so we start with deduction, right? And I would almost say that most of the things I can imagine putting on a proof are kind of implies, and then so you start with the deduction, right? And you might say, well, why didn't you give me assumptions and something to prove, right? And in some ways we did. These are kind of our axioms. You can see them up there. And this is what we want to prove. And we want to prove this from our axioms, right? So when I told you on a proof, on a test, I'm going to give you a bunch of axioms and something to prove, I might do that. But now that I think of it, I'll probably instead say the end of your axioms gives you what we're trying to prove, right? Everybody see it's the same? How are people doing? Are you guys following? I'm going a little fast because we're behind and I got mad at getting here. Should we slow down? People doing okay? All right. Everybody see what we got so far? This is the cut rule. This is our assumptions. This is what we want to prove, right? And so then we come up here. What is that? It's an A, it's and. So what do we do with ands? We separate them, right? Now, if you study it, and I studied it for a while, I feel stuck, right? I don't know what to go forward. Now, you could say, actually, what to go forward is there's an or, and one thing you can do with ors is Is what? No, you can only separate ors if I know one of them's true and I know one of them's false and I get the other. But you can't separate an or. But ors are good for cases, right? I know one or two things are true, so I could do cases. And let's think about it another way. Well, you could just build a truth table, right, in which you try all, there are 3 variables, so there are 8 lines in your truth table, and you could try them all, right? And that's not very elegant, but, right, we want a proof that sort of does all cases at the same time. But if we can't do that, maybe we can just do one branch of the branch, Davis-Putnam branching tree, right? You know what I mean? And that's sort of proof by cases. So, right, normally when you're doing Davis-Putnam, you set one variable, right? And if you say the variable's true or the variable's false, right? But here, well, knowing what the branch on, actually the truth is you could have probably branched on anything and it would have worked, right? I choose to branch on, oh no, here I am. Sorry, I was confused. Here I am actually branching on P, right? I choose, P is the cut variable, right? So I'm branching on what value P has. Does that make sense? So how do we, in order to do cases and branch on P, you need to do proof by cases, you need the or, right? You need that one of your cases is true. So how do you get the or is by bringing in the excluded middle. All right, people with me here? You're a little lost is, right, we assume this stuff down here and we're trying to prove this. And we didn't know what to do. So we decided, oh, these aren't ors. These are, yeah, I guess they are ors. We could have branched on something here. But we decided to branch on the value of P. Right? Why did we branch on P? Well, because P's in both of our things. Right? And so knowing P really gives us a kickstart. Right? And so we're going to say, well, it's okay to branch on P because we know either P is true or not true. And so then we're going to have our 2 cases. When P is true, we're going to have to prove what we want. And when P is false, we're going to have to prove what we want. All right, people good? All right, so in the first case, if P is true, you got to look up. We got line 3 and line 4 that we could use, right? And remember how we use an or? You know, 2 things are true. One this is true or this is true. How can you? What's useful? Right? If you know one of these is true, right? And what? Here you know the first one is false, right? People see that? Here are 2 things, not P and R. And here we know that not P is false. So what does that give us? That gives us that the second one is true, right? Using selecting or, right? Yeah, tells us that R is true. Now, where do we want? We want to get this guy down here. How do we get from line 8 to line 13, right? Line 13 is saying R or Q are true. If you know R is true, how do you prove that either R or Q is true? Is it true? Is ours true? Remember what I called it in the purple table? We got something little, and we're building something big, right? Or we have the value of R, and we're evaluating, right? I really think everybody should start memorizing the purple table, right? So how do we do this? Well, remember, you look at how do you prove an OR? Well, one way of proving an OR is if you know that one of them's true, then you automatically get the OR, right? In fact, we did that. One of our early slides was saying, suppose I tell you that you love logic, right? Then I know that you either love it or you do it, right? Does it make sense? So here we can say, how do we get this line here? Here, how do we get this line? Well, we built from 8. Right? Everybody see here, from 8, you can build this. Right? People good? And then now we do it again. Right? Knowing not P and this, you use the selecting and it gets Q. Right? And then knowing Q is true, you can build and get the OR. Right? All right, now what do we, oh, in fact, now how do we get this statement down here? Oh, so now you got it from either, both cases. And so we're done. Right? How are people feeling about this? You guys in the back? So if you're wanting to know how to study, and I would start now, first off, get that purple table deep in your soul, right? And then take statements like these and try to prove them, right? And I just made these up, right? I guess the way I made them up is I knew, I mean, you could try to make them up too. You could say, hey, I want to have a proof where I use this rule and this rule, right? What can I prove using this rule and this rule? I mean, that's what I did. All right. This was on it's written up. It was written up, so there is a question on the practice test having to do with parity here. And somebody was showing it to me and was kind of confused of what was going. One, they had more time than on a test because it was during COVID. Everybody was at home. Also, I wanted them to work through the concepts kind of on their own, but give them hints. And so some of the questions, if you look at the question, you'll think, I don't know what I'm supposed to answer here. And the reason is because the answer is so obvious. All right? You think you don't know how to answer it because it really, really, really is easy. All right? So sometimes when you think, oh, it can't be that easy, sometimes it is. All right? So this is just looking at parity, right, which says either they're both true or they're both, one's true and the other's not, or the other's true and the other not, right? We have an odd number of them, right? So what does parity say? It says alpha's true and beta's not, right? Or alpha's not and beta is, right? People see that? So here we have the simplifying rule, where if you plug in alpha, then you can simplify it to what? Everybody think right now. Suppose I know that alpha parity beta is true, and I know that alpha is true. Beta's false, right? In fact, here maybe this isn't what maybe I don't know this. This is what I need, right? And whether it's true if and only if beta's false, right? People kind of see that, right? If alpha is true, then this statement is true, right? If this is true, this is false. If this is false, this is true, right? People getting that? All right. So then there's a statement. What are we trying to say here? We're trying to say, if you know alpha is true, then you know that the parity is true if and only if beta is not true, right? People kind of follow that? That's what we're saying here. Can everybody read these? Right? The first thing when I say that you have to do is learn the purple table, but you also have to be able to read these, right? All right, so we don't have too many rules. The purple table doesn't even mention parity, right? So we have to translate it into ands or ors. And then how do you prove an if and only if? Well, you go in both directions, right? So this says, if alpha is true, then the thing that says parity implies not beta, right? And if alpha is true, not beta implies the thing that says parity. People, you good? Right? So we can prove these. And maybe I'll leave it for you to sort of trace through them yourself. They're very similar to our last proof, right? And then we can go in the other direction, right? We can prove the other one, right? So this is on the homework, so you can try it, right? And if you don't follow it, you can come and look at the slides, right? Not to mention the solution set. All right? All right, so remember this statement here? This was the statement where alpha says that I'm going to do well at school, and beta says that I follow my father's rules, and the left-hand side says either my father promises that either if I do well at school, he'll love me, or if I follow his rules, he'll love me, but he doesn't know which is which, right? And that's the same. Oh, that's wrong. That's an and. So here we do know which is which. He'll do both of them for you. All right? Everybody holler when I get and or wrong, right? This is the one where he will be happy with either of these. This is an and. He'll do this for you, and he'll do this for you, right? And if he'll do either for you, then it's okay for you to do one of them. You get to choose which one, right? Because either will make him happy. This one's an and.
If I follow this rule, he will love me.
Yeah. Well, this is why this is complicated, right? Your father is promising you, he has an and, so he's promising you two things. He doesn't know whether or not you're going to follow his rules. He doesn't know whether or not you will do well at school, right? You're just being born. And when you're born, he promises you two things. He says, if it happens to be that you do well at school, I'll love you. And if it happens to be that you follow all my rules, then I'll love you, right? So you as a kid Do you have to do both of those things? No, because either if you follow the rules, he's promising to love you. And he's promising, right? I mean, that's the, right? This is the why it's tricky, yeah? Yeah, yeah. All right, so this is his contract. Yeah? Yeah, yeah. All right, so this is an and he's promising this is true and this is true, right? Now, no. Okay, let's think about this. All right, yeah? Exactly. Exactly. And what was that word? And antecedent? Is that the left-hand side? Is the right-hand side? Which is precedent. Oh, these are words I don't even know. Pre and anti. Precedent and antecedent. All right, that makes sense. All right, so anyway, all right, so let's think about you as a kid, and you know, oh no, you're the father for a minute. You're the father. You have to make sure that the contract's filled. And how do you make sure his contract's filled? Is you have to have both implies to be true. And if the kid doesn't do well at school, then as said here, this first thing is automatically true, right? If alpha is false, then this is true. And the father doesn't have to do anything. If beta is false, this is true. And the father doesn't have to do anything. The father could love you or not love you, right? Hopefully the father still loves you, but he's not required to, right? Except your mom would be mad at him. All right? Now, if alpha is false, but beta is true, now to fill the contract, he has to make gamma true. Right? So here, this is what the kid's doing. The kid's saying, I get to choose whether I do alpha or beta. If I do alpha, my father's promised both of these. So if my father's promised that if I do alpha, he'll give me gamma, right? And here, if I do beta, then he promises me that if I do beta, I'll get gamma, right? So either way, I get gamma. Everybody good?
Professor,
and why
I have
we're
a
doing this
question.
one again? Because it's right somewhat with the father. It helps with our intuition. It has somewhat it doesn't help with our intuition, right?
Professor,
Yes.
isn't it false because it's an and, so you would have to have alpha and beta, not alpha or beta?
This one, you're saying this is not an if and only if?
Yeah, like I'm a little bit confused because on the right-hand side, it's saying alpha or beta implies gamma. So suppose alpha is true and beta is false, and that like alpha implies gamma. Then on the left-hand side, it would have to be an or, not an and, no?
Yeah. So some people's intuition says that if this is an and, this needs to be an and some people's intuition says they need to be opposite. And it's the opposite. If this is an and, this has to be an or. And if this is an or, this has to be an and. And one, we're going to prove it in a minute. But 2, the intuition is let's play the game as follows. The kid first chooses, right, whether to make alpha or beta true. And if he makes one of them true, he's just going to say, hey, I'm going to make alpha true, right? So now we got to prove that gamma is going to be true, right? How are we going to prove that gamma is true? Well, he makes alpha true and he makes beta false, right? Now we come over here, beta's false. So we have to say the father has to make this contract true, right? So with beta false, this thing here is true no matter what. But with alpha true, the father has to make gamma true. And so with alpha or beta, you get gamma. Does that make sense?
Yeah, thank you.
Assume it's the same. He'll yell if it's chat. I think it means Modus Ponens. Yeah, that's the one. You can use that if you want. All right. All right, so now let's see if we can prove this. All right? How have we proven it so far? Remember what, in fact, we gave a truth table with all 8 values and we saw that they were the same. We did Davis-Putnam, where we branched on the value of gamma. I think back then it might have been A, B, and C. Doesn't matter, right? We branched on the gamma, and then we proved it, right? And now we're going to see what we're going to do here. And actually, probably, again, we'll branch on the gamma, right? But we need to prove an implies. How do you prove implies, everybody? Deduction, right? You assume the left, and we prove the right. All right, now we have an and. What do we do with our and? We separate them, right? Now we have to, here's another implies. How do we prove this implies? Deduction, right? So now we've, right, these guys separated. Now proof by deduction, we're trying to prove this. How do we do it? We assume the left and we have to prove the right. All right? Now, what rule should we use now to get, oh, look at, here's a hint. We got no more lines, right? Because I counted them, right? In fact, I made this proof a previous term, and then this term, I separated them into order. All I did is change the order in which we do things. All right? Anybody want to see how can we use 3? What do we got? We got 3, 4, and 6, and we got to get 7. It has an or in it. Purple table. Yeah. Nope. Cases. Cases. This is exactly cases, right? You know that either alpha or beta is true. You know that alpha gives me gamma. You know beta gives me gamma. So what do? I get gamma using rules, lines 3, 4, and 6, right? Everybody see this? It's just this father thing. It's just really one application of proof by cases. Everybody good? All right, so now we're going the other direction because we want to do an if and only if, right? Here, this is saying if the kid chooses, he gets loved. And here, that confirms that the father's contract, right? So how do we do it? It starts with right? You see here, I put in the brackets for you, right? With the brackets, it helps you know left side, right side. And so what do you do with that? How do you get that? You do deduction, all right? And now what we have here, that's an and, right? How do you prove an and? Yeah, it's sort of separation backwards, right? If you know an and, you can separate them. And to get an and, you have to prove both of them and then build. Right? Everybody good? All right. How are we going to prove this implies? How do you prove it implies? Deduction. Right? So here we have to prove alpha gives me gamma. So here my goals from this, all we have is 2. And from 2, we have to prove that alpha gives me gamma. Right? How do you prove it? You assume alpha, and then you go ahead and prove gamma. Right? All right, so now we know, right, we got it from 2, we got to get gamma. So what are we going to do? Yeah. Yeah, I would say that's what we want to do, right? We know 2, we know alpha, so now we're going to do 2 is going to give us modus ponens. But what's the problem with that? What was your word? Precedence. It's not alpha, right? Everybody see what's happening here? That's why I circled it. It really looks like how are we going to prove gamma is we're going to use modus ponens, right? In fact, this is what I'm going to say here. Modus ponens is going to do it. So how do I get modus ponens? Is, well, if I can prove this, I can get gamma, right? It's just asking for it. I need to get gamma. I got this. What is this asking for? Modus ponens. Well, to do modus ponens, I need this, right? You need to build it. How do I get this? Well, I know one of them's true, and hence the or is true, right? And remember when I kind of was talking through the logic of it, this is more or less what I said, right? It says, right? I said, well, suppose the kid chose one of them, right? Well, if he chose alpha, well, then he's going to get gamma, right? I mean, that's, everybody good? Oh, here I kind of lied to you. Are we done? We got to redo it for B, right? We got to redo it for 8. And yeah. Oh yeah, here. Oh, there it is. I did finish it. Yeah. In fact, last class I think it was, I said what this is called. Proof by generalization, right? The thing's symmetric. And if it's really symmetric, it's nice to notice that, right? Everybody good? All right. Now, I say this, I try to make slides in case I have to teach 1019 again. And if anybody has anything to help me here, you know, this is just clearly wrong, right? Because in 1019, I think we got like 2 weeks to do all the proofs with the for alls in there, right? So I got to figure out, if I'm teaching 1090 again, I got to figure out what we're teaching, right? Clearly we can't do all of this, right?